Good afternoon, everyone. As you might already know, Wi-Fi devices use a protocol called WPA2 to secure the communications over the air. About 4 months back, it feels like a long time back, but about 4 months back, a few researchers from Europe published a paper pointing out some vulnerabilities with WPA2. Even the mainstream media picked up on this and wrote lots of articles about KRACK. Some of them were accurate, some of them were not so accurate. I'll take the next 30 minutes or so to give you a brief overview of what this KRACK is all about. Here's the outline of my talk. I'll first start by introducing what I call as 2 cardinal rules of encryption. Once we understand these rules, we'll be able to appreciate the loopholes that this KRACK attack exploits. And then I will talk about what countermeasures need to be taken to address these loopholes. And I'll also spend some time talking about the real exposure of this attack. And I'll finally conclude by talking about how the industry and the Wi-Fi Alliance is reacting to this. Here is my first rule of encryption. The rule is you should never ever accept an old packet again. I'll talk about this, I'll explain this with an example. Let's say I have a temperature sensor at my home. And when the temperature drops, the temperature sensor sends a message to the access point. The access point picks up the message and then passes it to some logic that's sitting behind the access point. Upon receiving that, the logic cranks up the heat. Obviously, this has to be encrypted, otherwise some malicious device can come and send this temperature is low message and my home will get, the heat in my home will keep going up. Just encryption is not sufficient. Let's say a malicious device comes into my home and then records this temperature is low message that's coming out of my sensor and then replays that message. And let's say it keeps on replaying it again and again. Then the logic will keep picking up this message and then keep cranking up the heat. So to prevent this replay attack, what the encryption standards typically do is introduce this concept of packet number. And let's say I received the last packet I received had a packet number of 10. I know that the next packet is going to have a number 11 or higher. So if I see 10 or lower, I'm going to drop that packet. Okay? So this prevents the replay attack because if I recorded the message, it still is going to have that same old packet number, and the logic recognizes that it's a replayed packet and drops. Okay? But let's say somehow I trick the AP into resetting the packet number. Then somebody can replay that old packet again and heat up my house. Okay? So keep that in mind, because this is what KRACK is going to do. It will somehow trick the devices into resetting the packet number. The second rule is we should never transmit 2 different packets with the same encryption key. This again I'll explain with a simple example. Let's say we play a game and I ask you to think of a number, and you don't tell me the number, but you add something else to it and then tell me the number. So when I hear this x plus z, x is the number that you thought of, z is that arbitrary number that you added to it. If you tell me x plus z, there's no way I can guess x because I don't know what the z is. And I don't know what x is either. And again, I ask you to do the same. You thought of y, you added z to it, and you told me y plus z. I don't know either x or y. But let's say the 10th number that I know that the 10th number that you're always going to think of is 42. Then once I have that known number, then I can work backwards and figure out all your numbers, because once I have this known packet or the known number, then with the easy math I can figure out everything. Okay? This is applicable to any Wi-Fi packet or any packet for that matter, any encrypted packet for that matter. If the information is getting encrypted with the same key, somehow I know that one of the packets is some known ARP packet or DNS packet or something, and I know some of the fields there, then I can work backwards and start figuring out the other unknown packets. Okay? So the basic rule is the transmitter needs to keep on changing the encryption key. One way, or the typical way this is accomplished is there is an unknown key, and then you manipulate that unknown key with the packet number, because every packet is going with a new number, and every time this manipulated unknown scrambler key plus this packet number is a new number, and then it keeps on changing. Both the transmitter and receiver know how this is all going to work. So that way, I am encrypting different packets differently. Okay? Here again, the key thing to notice is the whole logic relies on different packets having different packet numbers. And again, if I somehow manage to trick the device into resetting its packet number, then I manage to make the device transmit two different packets with the same packet number, the same encryption key. And then somehow I can work backwards and figure out what is going on over the air. Okay? So like I said, it's all about tricking the devices into resetting the packet number. Okay? All right. So let's talk about how we can trick a client into resetting its packet number. Okay? For this, we need to understand what I call as a ePole or a four-way handshake. When your phone connects to the Wi-Fi network here, one of the steps it goes through is this four-way handshake. Okay? This is the process through which both sides agree upon how the encryption is going to be done. The way it works is the access point sends something called a message 1. The station or your phone responds with a message 2. And then in response to message 2, the access point sends a message 3. At this point, what your phone does is it goes and installs the key. This is the key it's going to use for all its encryption. Okay? This typically happens at the start of a session. So an obvious thing to do is at that point go and reset your packet number. Okay? And then the client responds with the message 4. This is a thing that always happens. Okay? What these KRACK guys did is, the access point sends a M3 or the message 3. I know that at this point the packet number is going to be reset. The key gets installed, packet number is going to be reset. The client transmits M4 back. Okay? Somehow, a malicious device in the middle manages to suppress this M4. Right? This can be done with the man-in-the-middle attack. I'm not going to go into that aspect of it, but for this talk, let's assume that somehow a malicious device manages to suppress this M4. What the AP is going to do is it did not receive M4. So it assumes that the client did not receive M3, and it's going to transmit M3 again. At that point, the logic, the software on the client side, what it's going to do is it receives M3 and resets the packet number again. It just resetted the packet number, and then the way it's going to work is M3 comes, and then the client thinks that I'm all set with my encryption key. I'm going to start transmitting my data packets. The data packets are going to the AP. The man in the middle is picking up those data packets. And also, in parallel, what it did is it suppressed the M4. So because M4 got suppressed, AP is going to send this M4 again. Then the client is going to reset its packet number and then continue transmitting packets. What ended up happening is my initial packets went with the set of encryption keys based on the packet number. M3 got retransmitted, the packet number got reset, and the subsequent packets are again getting transmitted with the same encryption key. This is violating my rule number 2. So now the man in the middle can somehow look at these two packets, and if one of the packets happens to be known, it can figure out what the other packet is. Okay? So the workaround is very simple. The patch that probably most of you picked up is doing a very simple thing. This is a patch that needs to go into your phones and every station device. The right thing to do is if M3, if I know that I just received an M3 and for the same session, without receiving M1, M2, I'm receiving M3 again, don't reset the packet number. You don't even reinstall the key. Okay? So that's why this attack is called key reinstallation attack. Basically, we are tricking the client into reinstalling the key, and that's what caused this whole vulnerability. Okay? All that the patch does is, on the client-side patch, all it does is, it makes sure that if M3 is re-received, it doesn't reset the packet number. Some of the devices, in an enterprise setting, you cannot assume that everybody walking into the room will have the patch ready on their client side. So some of the AP vendors also provided a workaround for this. So the workaround on the AP side also is very simple. If M3, if the AP realizes that M4 did not come back, it doesn't just retransmit M3. It starts the process all over again, goes through M1 and M2. If I retransmit M1 and M2, if you go through this whole process again, the encryption key completely changes. That's how this protocol works. Okay. So that way, I'm making sure that two packets are not getting transmitted with the same encryption. Okay. But the penalty is, let's say the network is very crowded. Sometimes genuinely M3 gets missed. Now, every time that happens, I have to go through M1, M2 exchange again. So the connection establishment might take a little longer, but it makes sure that the network is protected. Okay. So that's the client-side vulnerability. And let's switch gears and talk about the AP side vulnerability. The AP side vulnerability gets exposed during what we call as fast transition. Okay. You probably had Wi-Fi link established, and you walked from the other end of the room to this end of the other end of the building to this end of the building. When that happens, your connection gets handed off from one AP to another. Okay. The typical process is every time the connection gets handed off from one AP to another, you have to go through this authentication process again and make sure that all the credentials and security keys are established properly. But to make this process faster, Wi-Fi introduced a scheme called fast transition, where a similar vulnerability exists. Okay. In this fast transition process, there is this packet called reassociation request frame. Whenever this reassociation request frame is received, the AP resets its packet number. That's the vulnerability that's getting exploited. Again, we are tricking the AP into a device into resetting its packet number. The next slide basically goes into some more details on this. When this fast transition happens, there is a couple of authentication exchanges, and then this reassociation request, reassociation response frame gets exchanged. Okay, the reassociation request comes from the client to the AP. So all that the device in the middle has to do is record this reassociation request frame. Okay, and then it remembers that message. The client keeps sending messages, and at some point, all I have to do is just replay that reassociation request message. Okay, so that's a very special packet. It doesn't have any encryption. It doesn't have a packet number per se. So the AP will just pick up that packet, and once it receives it, it again resets the number. The malicious device recorded all the packets that came. It can start replaying it now because the packet number has been reset with this reassociation request message. Okay. For this, you don't need anything sophisticated. All you need is a device that can record the messages and play back. You don't need any sophisticated man in the middle that has to do anything clever. Okay. Again, the fix for this is pretty straightforward. A quick workaround for this is disable this 11R, because 11R is the one that is exposing this vulnerability. And most Wi-Fi access points or routers have an option to disable 11R. Once you disable 11R, this vulnerability goes away. This is the quick workaround that was proposed initially. But the right thing to do is, if the reassociation request comes, and the AP should not reset its packet number. Okay. So we basically talked about, what is the loophole and how this loophole needs to be addressed with these fixes. Let me I have one slide that basically talks about the exposure, the real exposure. Okay. So to be able to execute this crack attack, you need a fairly sophisticated hardware and software, especially to expose the client-side vulnerability. You need a man in the middle that is simultaneously receiving packets from the client and playing it back to the AP. Okay? As you know, most of these wireless devices are half duplex. They cannot transmit and receive at the same time. So you need some fairly sophisticated hardware that can simultaneously transmit and receive. They should not interfere with each other. They need sophisticated antennas. So a pretty complex hardware is needed to execute, especially the client-side attack. Okay? And then the other thing is, this is not an attack that somebody that is sitting in another continent can execute. They can execute, but they need to make sure that this malicious device is sitting within the building. So somebody has to take this device, put it inside the building, otherwise this attack cannot be executed. Okay? And some of these articles, the mainstream media articles, try to project as if there is an app that you can download and start executing this attack. That's not true at all. Again, it is a pretty complex way. You need a sophisticated system, sophisticated software, hardware to execute this attack. Most of these enterprise access points have this feature called wireless intrusion prevention and detection. Basically, if there is a man in the middle, there are ways to detect the man in the middle and then make sure that no client connects to the man in the middle. Okay? So if that is the case, if that logic existed, there is one more hurdle to executing this attack. Then, even if you manage to execute the attack, you cannot inject or forge a packet. All you can do is decrypt or replay packets. Okay? And then there is no way to get to the encryption key or the password. And then for all this to happen, so like I said, this ePole exchange is the phase during which this vulnerability gets exposed. And this ePole exchange happens once in a session. There is this narrow window during which these packets get exposed, and that's where the vulnerability happens. So you have to be monitoring all these. A malicious device has to be able to capture the packets right at that moment to execute this attack. Same thing with fast roaming as well. It doesn't happen forever. Only when somebody goes from one AP to another, that's when this particular phase happens. Yes, it is a vulnerability, and everybody needs to fix it, but it's not as bad as what some of the mainstream media projected. Okay. Here's my final slide. As I said, it's all about tricking the AP or the client into resetting the packet number, and this happens when the key reinstallation happens, hence the name key reinstallation attack or crack. And by this time, as I said, it has been 4 months. Most of the vendors have released patches to address this loophole. Most of you might have already installed all those patches. And Wi-Fi Alliance, which is the industry consortium that is taking care of this Wi-Fi, they've added additional tests to WPA2 certification to make sure that this vulnerability doesn't exist in the software implementation. Okay? And also, recently, WPA3 got launched by WFA. So this is making some of the security requirements tighter, and that hopefully will make sure that such vulnerabilities do not happen in the future. That's all I have. Any questions or comments on this? All right. Hopefully I was very clear then.
Sounds very clear.
All right.
Let's thank the doctor again, Dr. Sankari. Thank you very much.
Thank you.
Appreciate it.